Hello everyone. Today we are covering a topic from IGCSE Cambridge Physics, lesson Motion, Forces and Energy, topic Energy, Work and Power, subtopic Energy Changes. Energy can take different forms. For example, there is chemical energy. It's a type of energy in food, fuel, or even electrical batteries. And there is kinetic energy. It is the type of energy in every single moving object. That is gravitational potential energy. It is the energy when an object is raised above the planet's surface. There is elastic potential energy. This is the type of energy in objects that are stretched, compressed, or twisted. Internal energy, or more popularly known as thermal energy, is the energy in any object that is heated or any object with some sort of a temperature. Magnetic energy is when there is a magnetic field in an object. Electrostatic energy or electrical energy is caused by the electrostatic forces between charges. Then there is also nuclear energy, which is because there's forces acting between atomic nuclei. Now, these are not the only type of energies. These are some of the energies that you will come across in this syllabus. Energy forms change from one to another all the time. For example, let's look at an instance where we throw a ball up in the air. When the ball is just starting to move and not gone above the ground level, it doesn't have any gravitational potential energy. It just gained a bit of velocity. So it will only have kinetic energy. At the bottommost position of the ball, the kinetic energy would be maximum because of this. And as the ball moves up, what happens is the ball will slow down. The velocity will decrease. And because of this, kinetic energy will also decrease. But since the height of the ball has now increased, it's further away from the ground, the gravitational potential energy here has increased. Gravitational potential energy increased, the kinetic energy is decreasing. So what really happens is the kinetic energy that was previously there, maximum kinetic energy that was previously there, has transferred or converted into gravitational potential energy when the ball is moving upwards. Eventually, the ball will reach the maximum height it can go to. And at this point, the gravitational potential energy is at a maximum. And at this moment, the ball will come to a momentary stop, which means there will be no kinetic energy. So there will be minimum kinetic energy at the topmost position, while there is maximum gravitational potential energy. And once this happens, ball will start coming down slowly. Now, the height of the ball reduces while the velocity starts increasing. The ball will start falling down faster and faster. Now, when it's falling down, gravitational potential energy decreases while the kinetic energy increases. Once again, it will come to its original position on the ground where it will have minimum gravitational potential energy and maximum kinetic energy. Another good example for energy changes is a filament light bulb. In a filament light bulb, we supply electrical energy. This electrical energy is converted into light, also some heat. Let's look at another example, a bungee jumper. Now, usually in bungee jumping, what we do is we go to a very high place and the person would be bound by an elastic rope and they will jump down. So at the point where the bungee jumper is just about to jump, he would have the maximum gravitational potential energy. because he is at a top position. Now, when he starts falling, that gravitational potential energy will be converted into kinetic energy because he'll be falling with some sort of a velocity. And at the bottommost position, the elastic that is bound will be completely tight. So that means the kinetic energy is converted into elastic potential energy. So at this lowest point, the jumper's gravitational potential energy will completely be converted into the elastic potential energy of the cone. The principle of conservation of energy is the universal law that governs energy transfer. It states that energy is neither created nor destroyed. It can only be transferred. Now, energy can change from one form to another, but the total amount of energy in the universe is always equal. No new energy is created and no old energy is destroyed. Total sum of energy remains constant. All the examples we discussed previously, the filament lamp, the bungee jumper, the ball being thrown upwards, all of them are examples for principle of conservation of energy. Now let's look at another example, simple pendulum. When you swing a simple pendulum and it's at the edge where it's at the topmost position, the kinetic energy will be zero because the simple pendulum will come to a momentary stop. And at this point, the gravitational potential energy will be maximum. And when it starts swinging back again, the gravitational potential energy will be converted into kinetic energy. And at this middle position, it will have maximum kinetic energy and minimum gravitational potential energy. At all times, at all positions of the simple pendulum, the sum of kinetic energy and gravitational potential energy is a constant. Kinetic energy and gravitational potential energy, the sum is a constant no matter where the simple pendulum is and how it is swinging. We all know energy transfers from one energy store to another. Chemical, kinetic, gravitational, elastic, thermal. Energy transfers between these energy stores. And this transfer happens by using four key pathways. Firstly, mechanical. For example, when gravity accelerates an object and increases its kinetic energy, that would be a mechanical transfer path. Then electrical. Electrical is whenever current is involved. So when a current passes through a lamp and it emits light and heat, that is an example for an electrical pathway. Heating is when a temperature difference is involved. So for example, when a fire is used to heat up an object, that is using an electrical pathway, a heating pathway. And finally, we have radiation. Radiation, as an example, would be vibrations causing waves to travel through air as sound or an object emitting electromagnetic radiation. Radiation will be discussed in more detail in the waves lesson. Now let's look at a few types of energy. In this lesson, we will be mainly looking at mechanical energy types. In future lessons, we will learn about other types of energy in detail. First, we look at kinetic energy. Kinetic energy is the energy in an object as a result of mass and speed. So whenever an object is moving, it will have kinetic energy. Kinetic energy is given by the equation half times mass times velocity squared. So Ke is equal to half mv squared, where m is the mass of the object in kilograms, v is the velocity of the object in meters per second, and kinetic energy given by joules. not just kinetic energy, any type of energy is given by joules, capital J. Now let's look at gravitational potential energy. It is the energy on an object as a result of gravity due to its height. Now, when an object is above the ground level, because it's working against the gravity, it will store gravitational potential energy. When the gravitational store of the object is raised, then the object will store the gravitational potential energy. And when the gravitational store falls down or is coming back to the ground level, then the gravitational potential energy will be transferred to a different energy type. Gravitational potential energy is given by the equation mgh, where m is the mass of the object in kilograms, g is the gravitational field strength. So in the IGCSE context, the gravitational field strength will always be 10 newtons per kilograms. And h is the height in meters. And of course, gravitational potential energy is always given by joules, the units for energy. Now, gravitational potential energy is dependent on mainly the height and the mass of the object because g is a constant. G is always 10. The higher the object is, the higher the gravitational potential energy is. We all already know about the law of conservation of energy. Energy can only be transferred. It will not be created or destroyed. This means overall level of energy in a closed system is a constant. But let's look at an instance where we're trying to light a filament lamp. Is all the energy we give in electrical form converted into light? No, right? What happens to the rest? Does it just disappear? Of course not. That's against the law. What happens is some of the electrical energy that we give is lost to the environment as heat. Some of it is wasted as heat. So in real life, we can't convert 100% of the energy to what we want. Some of it will be wasted to the environment. Usually, it is lost to the environment as thermal energy. This radiation that is lost to the environment can be heat, light, or even sound. What happens during energy transfers can be represented in flow diagrams. This diagram right here is known as a Sankey diagram. The arrows represent the flow of energy. The usable energy is always shown by the horizontal arrow, this one right here. And the arrows that are curving out from the horizontal arrow is the wasted energy. The width of the arrows represent the amount of energy that is usable, wasted, or in this case, at the very beginning, the width represents the input energy. So in this example, we have the energy transfer of a vehicle. The input chemical energy is 10,000 joules. For example, if we use a scale of 10 kilojoules represented by 1 centimeter, we could draw this arrow with a width of 10 centimeters at the beginning. Out of this 100,000 joules, 60,000 is wasted as heat and sound. So The width of this arrow should be 6 centimeters, representing 60,000 joules. The usable energy at the end is just 38,000. So that means 2,000 is wasted as lights, radio, and for recharging battery. So this 2,000 joules can be represented by an arrow width of 0.2 centimeters. That leaves us with the 38,000 joules of kinetic energy, or the usable energy. This can be represented by an arrow width of 3.8 centimeters. So as you can see, always the total energy in is equal to useful energy out and wasted energy. Now that we have covered the theory for this topic, let's have a look at some past paper questions. A space shuttle of mass 35 kilograms is traveling in a straight line at a velocity of 1,200 meters per second. Assume no external forces act on the space shuttle. Calculate the kinetic energy of the spacecraft. Now, since they have mentioned that there is no external forces acting on the space shuttle, we can say that the velocity of the space shuttle is constant. So in that case, this question becomes very simple. We just have to use the kinetic energy equation to find the kinetic energy of this space shuttle. Kinetic energy is equal to half mv squared. The mass of the space shuttle is 35 kilograms and the velocity is given as 1,200 meters per second. Now, when you plug this into the calculator, you should be getting a value like this, 252.00000. Now, because this value was a bit too big, we need to keep it in the scientific form. And also because all the answers are in the scientific form. It's pretty clear the answer should be 4. But to convert this into scientific form, let's see how many places we have to bring 4. 4, 5, 6, 7. The answer should be 2.52 times 10 to the power 7 joules. Answer number 4. We'll look at one final question. A ball is dropped onto a hard cement surface and bounces. It does not bounce all the way back to where it started, so has not regained all of its original gravitational potential energy. Which statement accounts for the loss of gravitational potential energy? Let's have a look at the statements. The ball doesn't bounce all the way back. Why? Because some of the gravitational potential energy is lost. First thought, is the gravitational potential energy lost because the energy was destroyed? Of course not, because the law of conservation of energy states that energy cannot be destroyed or created. So we can eliminate statement 3 and 4, which has the word destroyed, because energy cannot be destroyed. 3 and 4 cannot be the answer because of the word destroyed. Out of 1 and 2, the internal energy or the heat of the ball and its surrounding has increased, or the chemical energy and the elastic energy of the ball have increased. What can be the correct state? First thing, the ball would not possess any chemical energy since it's not a food source, nor a fuel source, nor a battery. The other thing is, usually when there is a loss of energy to the environment, it is lost as heat, sound, or light. So the correct answer in this case would be answer 1. The internal energy or heat of the ball and its surrounding has increased. With this, we have come to the end of this topic. Thank you for listening.